Hello and welcome. My name is Anna Marie Antonozzi, and it is my pleasure to introduce the launch of our product, COVID Cough, on behalf of the team at Metadata Technologies. We have a full agenda to present to you today. We will begin with introductions, walk you through our business problem, objectives, and solution. We will review the modeling methodology, including an overview of our data set, processing, and final results. We then will walk you through our mobile application, including a demo of the app. And finally, we'll wrap things up by discussing our final conclusions and recommendations. So who are we? Metadata Technology was established in early 2022 by a team of data scientists from Northwestern University. We are a team that is passionate about utilizing the power of data science and machine learning technology to solve medical problems and improve the patient experience. I am an MSDS candidate at Northwestern, and I joined the team with a background in luxury retail, and I've worked in the B2B and B2C space for nearly 10 years. Sophie, our project manager, is also an MSDS candidate and has a background in neuroscience. Sophie brings experience working as a medical researcher as well as a marketing analyst to the team. Chris, our machine learning engineer, is currently a director at a financial services company in the New York City metro area. And he oversees data engineering, data management, and data analytics for the infrastructure services organization. Chris brings over 14 years of experience and has multiple patents in security, data management, and automation. Soon, our product manager is currently an enterprise architect at an electric cooperative in the DC metro area that provides health insurance for its member cooperatives. Soon brings over 13 years of experience within the financial services sector from also working as a business analyst and a project manager. And last, but certainly not least, Jody, our lead technologist, is currently a managing director of technology at Citibank. She leads the inventory developer and enterprise automation services group at Citi that uses data to drive automation and provides tools and services to the global development community. Jody brings over 25 years of experience in technology in enterprise architecture, security, and innovation. So how many times have you had a little tickle in your throat and wondered, is this COVID? Yet finding a COVID-19 test often feels like a scavenger hunt. As we know, COVID testing has been challenging and expensive over the last 2 years. Our team wanted to leverage the 5.29 billion mobile phone users in the world to deliver a simple, repeatable, and free preliminary COVID test. COVID Cough is an instant response app that diagnoses COVID by recording your cough. Utilizing deep learning models, COVID Cough distinguishes between cough sounds of COVID-19 positive individuals and negative individuals. This app is a simple tool to help patients make informed decisions on pursuing further COVID-19 testing or self-isolation. Did you know that insurance companies are required by law to fund 8 COVID tests per user per month? That's a total of 96 tests per year. So with 150 million privately insured individuals in the US, that comes at a $1.4 billion cost to insurance companies. COVID Cough will save insurance companies money since individuals can use our app to quickly determine if they need to seek out an official COVID test. Insurance companies could also integrate our technology seamlessly into their own mobile app to provide further COVID-19 recommendations.
And from here, this model. The business model is largely pretty simple, where we will be partnering up with insurance companies, and we will be providing a world-class diagnostic tool that will enable early detection and reduces wasteful testing for the various users and the participants in their particular health insurance pools. So we will be partnering with these insurance providers so that we can provide these early detection through our app, and in all, as Anna mentioned, reduce any wasteful testing that might go on, so that we could capture whichever symptoms that are COVID related earlier on. So our team has come together to create a proof of concept through the opportunity that was provided to us as a part of this capstone project. Obviously, these high-level estimates do not provide any labor and employment costs, but as far as other time and materials go, we provide an estimate of $9,500. Of which $4,500 will be dedicated towards modeling and analytics. And that would cover technology costs such as database, storage, server, and other cloud costs, as well as dashboard licensing, which will be mentioned a bit further on later. And we will also be dedicating $7,500 towards application development, for where it would also cover the database and storage costs, as well as other server related costs towards the application, as well as certain third-party integration fees that we would need to front as we are integrating with other technologies such as Facebook and Google and leverage their APIs. Additionally, another $7,500 will be dedicated towards legal fees and partnering up with marketers to help develop our product strategy and our marketing strategy, in addition to the legal fees that we would need to have in order for us to go about getting FDA approval, as well as getting incorporated for our entire team. Objectives here are pretty simple in that we would like to distinguish cough sounds between COVID positive and COVID negative individuals, and create a classifier using various models. I think we tested up to 10 models and find a primary classifier for our COVID-19 detection, as well as build a dashboard and mobile app that records the COVID-related cough, as well as provide some type of assessment on those coughs to see if they are COVID-related or not, and provide further direction on if they need to self-isolate or pursue other testing measures. As for deliverables, on a high level, we were thinking to provide an EDA of the cough sounds, as well as provide the machine learning model, and additionally the mobile app and dashboards. These are some of the distinct features or milestones that we wanted to provide as a part of each. I won't actually go into each and every single one of them, but at a high level for the EDA, we wanted to get a handle and get our arms around the information that was collected, as well as create that machine learning model for the classifier, and I guess go about investigating and experimenting with different dashboards of the data that we attained and modified, as well as develop out that mobile app that will ultimately interface with our customers. As far as timelines go, we began the class at the beginning of January, and from there we developed a team, and we had our first deliverable for the project provided on January 23rd for our project goals. And then we provided our preliminary findings and the initial findings on January 13th. From there, we refined our app as well as our dashboard to ultimately provide our final report that was due approximately a week ago. And we have been preparing the deck and this current oral presentation ever since. And as far as the data overview is concerned, we sourced around 20,000 crowdsourced cough recordings, and it had a variety of different demographic attributes. In addition, it had some data that was labeled, as you see in this table here, by experienced pulmonologists of more than 2,000 recordings to help train our models. Just to go through some of the labelings that they provide, it was quality, cough type, dyspnea, which is another way of saying labored breathing, wheezing, stridor. And stridor means there's some type of vibrating noise within the breathing, choking, congestion, nothing, diagnosis and severity. In all, there are around 4,000 healthy clips, 1,100 or so symptomatic clips, and around 500 or a little shy of 500 COVID-19 positive data points. So as many of you might wonder, there are different types of cough sounds. There is a dry cough and a wet cough. And I thought it would be a good exercise if we could try to differentiate between ourselves on which cough would be the dry cough or the wet cough. COVID-19 coughs are generally coughs that are dry. So Chris, if you could go ahead and go to the top recording and play that. There we go. That was cough 1. And that was cough 2. And cough 2 was actually demonstrated to be a dry cough, and the top cough was actually a wet one. So as you may have heard, there are certain different patterns associated with each one audibly. It might be obvious to some and not so to others, but there is nonetheless a way for us to go about delineating between the cough sounds.
Hello, everyone. My name is Sophie Angus, and I will continue discussing our data a little bit and then be jumping into our modeling process. So our team decided to experiment with using 2 platforms, Microsoft Power BI and Tableau, to create our dashboards, as these have been identified by Gartner as 2 of the 3 leaders within business intelligence and analytics. It was important for our team to try both the data visualization tools in order to determine which would provide the best visual experience for our users and insurance companies in the future. And I will show you these dashboards on the next slide. However, we ultimately decided that the Tableau dashboard was the most effective in communicating our data because the visuals are much more configurable and more pleasing to the eye. Tableau also had a wider range of visual libraries that helped us easily create powerful graphics that would immediately communicate the most important traits about our data. And it also had better performance with larger data sets, which is what we're using in this project. We did experience an issue with Power BI in that it only works with Windows, whereas Tableau is compatible with both Windows and iOS. So here are our two dashboards, the Power BI on the left and our final dashboard that we're going to move forward with on the right using Tableau. And they both show the same data. The top left quadrant displays the location of the collected data points in our data set. The top right is a heat map of the symptoms of all the cough recordings. And as you can see in the Power BI dashboard, there is no heat map present because we couldn't get any associated colors to work, and therefore no colored heat map. This is one of the major reasons why we decided to go through with the Tableau dashboard. The bottom left is the gender distribution of data points we have, and the bottom right is a stacked distribution of age delineated by COVID status. So as you can see, they present very similar data, but this Tableau dashboard will be a great implementation in addition to our mobile app, possibly in the information section, and will also be useful in future presentations to insurance companies about the data that we have used to build our models. So now I'm going to jump into our modeling methodology. And even before we were able to start our exploratory data analysis, we had to clean out some of the missing data in the data set because there's a large amount of metadata that Soon has just discussed that had missing values, some of them up to or over 50% of the values missing, and therefore these were not effective for us to use in our model building. So as we begun our exploratory data analysis, our first step was to listen to the cough recordings and decide which ones we could consider as quality coughs. And so we used two metrics to determine this. One is the signal to noise ratio, and the other is cough detection. And so we explored these. We found that a signal to noise ratio of 0 either had no cough sounds, had a lot of background noise, or did not sound like coughs at all. It could have been birds chirping. And this, of course, would not help our model perform well. And so we kept clips of a signal to noise ratio of above 10 as quality coughs. Similarly to the cough detection, we decided that a cough detection of above 0.7 sounded like a quality cough, and these were viable for our final data set. And on the right, the box plots we use to confirm these ideal values and also remove outliers. The next step was data pre-processing. We created spectrograms and male frequency septural coefficients that are shown on the on the left to visualize the signal strength over time at various frequencies. We also created wave plots that are shown on the right, and these are used to determine where to trim our audio clips to reduce the silence before and after a cough recording. So as you can see, the spikes are where there was sound and the flat lines are where there was none. And so we wanted to trim these clips to be only areas of, or only clips of sound. And we also trimmed all of our clips to be only 1.5 seconds long in duration to keep a consistent length. And our final data set consisted of 450 random samples of healthy, symptomatic, and COVID-19 cough sounds. And these are what we're going to use in our modeling data set. The next step of getting our data ready for classification was data augmentation. After exploring our data and our pre-processing, we discovered that we had a very limited amount and limited access to data points that were labeled as COVID-19 positive. This would most likely cause our model to overfit if we went through with this data set. And so to avoid this, our team decided to augment our data to increase the diversity of our data set. Now, data augmentation has 8 steps that we use as shown on the slide here. First, there's a time shift, then a pitch shift that modifies the frequency of the sound, a time stretch that slows down or speeds up the sound, adding extra noise, applying filters. We also shifted the silence in the sound to the right, adjusted the pitch and speed. And after all of these steps, we then augmented the audio clips by dynamically changing these values. And then these data points and audio clips that have been augmented were then used in our classification.
Now that we have a good set of data, the next step was to transform the data into a working format that could fit into a machine learning model. Anyone that has done some type of machine learning would realize or know that you can't really take an auto recording and plug it very nicely into any type of formula. It's not numeric, and you need to get the most important points out of the audio clip. One way to do that, and is one of the most widely popular mechanisms to do that in a machine learning model, is to convert the audio clip to a MEL spectrogram. A MEL spectrogram at a very high level makes 2 important changes that are relative to the spectrogram that you would normally get from a plot, and that is frequency versus time. That frequency versus time then provides a good visual depiction of the audio wave file, which then could be used as effectively images in of the audio recordings, and transforms that into something like any other image recognition model could interpret into classifying whether or not a cough is COVID or not. Another feature that we wanted to look at was how best to determine which target class or which label we should use that would give us the best model performance. In the data set, we had 2 different types of target classes. One was a cough type and one was a diagnosis. And one thing that we found after doing our initial training was that our model performance wasn't as high as we would have liked it. So we attempted to see if we could determine if there was a better target class to predict the machine learning model on. And we did identify one as the cough type as either being a dry or wet, given that a dry cough is known to be a COVID cough. And one way we determined this was we applied what we call a kappa fly score. A kappa fly score is essentially a method that determines how well people agree amongst each other when you have classification data where normal means and medians of numeric data are not really reliable. The interpretation really comes back with there's poor agreement, there's slight agreement, there's fair agreement, there's moderate agreement, there's substantial agreement, and there's almost perfect agreement. And what the kappa fly score showed us was that we, amongst the expert doctors that opined on the data set, that there was fair agreement on cough type where there was poor or slight agreement on the diagnosis. So this helped us determine the target class that we use in our machine learning model, and the cough type was effectively used in our subsequent training. So I want to take a moment to show the big picture or summarize what we've talked about so far on the modeling approach. We have our data set is comprised of cough recordings. We pre-process the cough recordings to trim it, to get rid of dead noise, filter out ineffective audio recordings that have like bird chirpings. We extracted features from the clips of the audio clips by augmenting the data to increase the data set and also converting it to a MEL spectrogram. And then we identified our target class that we were going to predict. So the modeling approaches that we took essentially were our traditional machine learning models and our deep learning models. Although most research pointed us at a convolutional neural network, we wanted to test different model types that have been used in machine learning in other audio examples. So on the machine learning model side, we tested the support vector machine, logistic regression, simple random forest, a gradient boosted tree, a key nearest neighbor, and a naive Bayes classifier. On the deep learning models, we tested a convolutional neural network, a deep neural network, a recurrent neural network using long short-term memory, a recurrent neural network using gated recurrent units. And all these models were tested against the MEL spectrograms that we generated and we evaluated the performance of those models using precision and recall, an F1 score, accuracy, an ROC, AUC score, and a PRC plot. Precision essentially will tell us how well our model was able to predict the target class that we were trying to do, which is the dry cough, and a recall measure was used to determine how accurate the prediction of a positive COVID cough was. And as you can see here, we summarize the various machine learning models that we tested out. And our findings were in line with what most researchers indicated, which is that a convolutional neural network provided the best performance in predicting a COVID cough. Overall, it had a 69% accuracy. It was able to predict COVID positive 68% of the time, but more importantly, of that 76% of them, of those positive predictions were correct, and it had the highest F1 score amongst all the other model types. One thing to note is that some of these machine learning models proved to be ineffective. For example, a deep neural network could not distinguish between a COVID and a non-COVID cough. The same issue happened with the support vector machine and also the naive Bayes. And our outcomes were in line with most of those researchers. Next slide.
Hi,
So,
I'm Jody Spearing, and I'm going to talk to you about the development framework for the application. And for this framework, we were using React Native with Expo as the primary CLI interface. This enabled us to really be able to have a single development track, but be able to support several different technology platforms, whether it's a browser, an Android, or an iPhone. It also supports things like iPads or tablets. There's lots of features and functions within the React Native framework as well to allow us to have consistency with that look and feel across those platforms. In the technology architecture, what we designed was around flexibility of the architecture so that we could support multiple authentication frameworks, whether it was a local one, maybe the insurance company would want to provide, or whether we wanted to be able to authenticate to a Google or Facebook authentication service. That capability allows us to be able to ensure that we are compliant with the HIPAA requirements for privacy for people that want to maintain that level of privacy. When we looked through the questionnaires, the health questionnaires CDC provides an applet that can be part of your app to answer and respond to the standard health questionnaires. The data then gets sent into the CDC directly from that applet. And from there, we can contribute to the wealth of data that the CDC is compiling. The Expo provides a publishing platform to allow us to publish the app for testing and for MVP exposure to select customers without going through all of the work that needs to be done to officially publish the app through the App Store, the Google App Store, Play Store, or the Apple App Store. That requires quite a bit more work, and we would definitely want to go through that as we launch the product into production. But for the MVP, it was too much overhead, and we wanted to be able to test in real time on real devices. The Expo platform allows us to share our app on all of those different platforms, and it provides a QR code. All you need to do is aim your camera at the QR code and install the Expo application, and you can directly load the app in a test mode to your phone. It also gets updated in real time as you are doing your development. So you can have your simulator and your emulator. So the simulator is for the iPhone, the emulator is for the Android, and your real devices all running your test at the same time as you're doing your development. That greatly speeds up the development lifecycle and makes it really clear where you have things that you've created that don't show up consistently across those different platforms. You do need to be able to accept the request to join the team, or you could make the app public through Expo as well. When we look through the experience for the users, we wanted to focus on the top 10 features that we would be exposing to the user. So a very simple interface, the authentication mechanisms I talked about before, the ability to support multiple profiles. So this is an important feature, especially for families where kids probably don't have their own phone, but you'd want to have separate profiles in order to have your kids have their own profiles with their own history. The link to the CDC website, like I mentioned, the ability to record up to 30 seconds of cough. Now that variation, as Chris was talking about before, would be dependent on whatever we thought was the most effective length of a cough and the number of recordings that can be stored. So we set it for 25 recordings, but that's fully configurable. We could run the models against the recorded cough that happens through an API and show the results instantly on the phone. We can also store the history of all of the previous results. And we can have info links to local testing centers, the CDC websites, other information, the dashboards that we talked about earlier, and information about the Medidata Tech company and the COVID cough application, including all of the wonderful data we just finished talking through about the development of the app and the feature extraction. So here is the prototype with several of the different screens. I won't go through all of these screens with you, but I think we can go into the demo. And I will share my screen. So this is the app. This is the minimum viable product app. You can see it has the logo of the app. We can click on that and we can go to the About the App screen. We can also have a guest feature. So if somebody does not want to save any data, they just want to be able to do the recording as a guest, we offer that functionality. It goes direct to the recording screen. I've already logged in, so I'm not going to log in here. It'll go right to the home screen. In the home screen, we have a series of recordings from previous actions. the recording one, you can see the details about the recording and what was the status of it. You can go back to the home, back to your listing. You can go into your account information, and in your account information, you can see the different informations, messages, if you want to have interaction back and forth with Medidata Technologies or with the COVID cough support team, and the recordings of the cough. And now we can just go back, whoops, and we'll do a recording. So from here, we can start the recording. Stop the recording. You can replay the recording. And then you can evaluate the recording. It will come back with the results in just a few seconds. Another thing that's great about this is that we can look at these results. Oh, here we go. And we can understand how this links back to the earlier conversations about the wet and the dry. So here we have the results. The probability that I have COVID is 60%, and the probability that I don't have COVID is 39.3%. So that is the demo of the COVID cough application. In summary, we have been able to put together, I think, a very, very profound project where we can leverage cell phones to provide at least a preliminary review of whether somebody should go for a more extensive COVID test, either a rapid test or a PCR test. And as COVID becomes more and more part of the regular yearly cycles like the flu, with tests like this, we won't have to keep up with every different variation in the same way. We can just release a new patch to the app instead of trying to keep track of which test works well for which type of COVID variant. And I guess I should go and do a COVID test myself, since it said that I had a 60% chance of having COVID. So thank you very much for your time.
To wrap the presentation up, we wanted to give a conclusion of the overall COVID cough application. So we look to address the pressing issue that faces not just the United States today, but the world, which is the lack of COVID-19 testing, especially as new variants of viruses emerged in the past and as they may continue to emerge in the future. We investigated this problem by leveraging a crowdsourced or an open source data source that contained about 20-ish thousand audio recordings. And we were able to create a learning model that would assess the wetness or the dryness of the cough recording. Our model suggested that a convolutional neural network was the best model type to go forward with. It consisted of 14 convolutional layers with 16, 32, 64, and 128 filters, 2 max pooling layers, and 2 dropout layers. All performance metrics were around 70% accuracy, and that the CNN model was incorporated into the mobile application demoed by Jody. With that said, we wanted to highlight some of the challenges that we faced in creating the MVP. The first one was there was a significant amount of imbalanced data between COVID-19 versus non-COVID-19, which caused us to have to pivot to leverage the dry versus the wet coughs. To put it in perspective, after doing all the data cleansing that Sophie walked through with removing bad audio recordings with birds in the background or bad cough quality, it really only left us with about 500 or so COVID audio recordings versus over 1,000 non-COVID recordings. So our recommendation or our challenges were to overcome that And the other side of this is that the feature extraction took a very long time to run. We leverage a Google Colab environment to develop it with a graphics processing unit. And some of the pre-processing and the machine learning models took days to process. With that said, there's cause for hope. Our prediction showed very promising results for dry versus wet, and we're confident that if we were to collect more data, we would be able to more reliably rely on the COVID classification, given that we had such good results with the dry versus the wet cough. And we could even do that by enhancing our mobile application. So we can how we can record a audio recording and evaluate it, but we could also record that and upload that into the cloud and increase our crowdsourced data source. This is something that could give any doctor in the world. Most doctors have a mobile application, and they could increase the data set by recording more coughs. We can move to the cloud more effectively and get more infrastructure, which will improve our feature extraction, especially as we get more data and the training time on the model. And our next steps really is to expand our client base, secure additional funding from the business, and work with the FDA for approval. With that said, that concludes our presentation.